This video is part of the series to accompany discrete mathematics and functional programming. I'm Thomas Van Drunen. Specifically, this video is the second part of a pair of videos on set operations and how to verify propositions about sets. The previous video corresponds to section 1.4 in the book, this video to section 1.5. Sets play an important role in computer science, some areas of math, and many applied fields of study. So understanding them and working with them is pretty crucial. But as far as I'm concerned, the most important role sets play in this course is as raw material for practicing proof writing. That is, once we start learning how to write proofs, most of the propositions we'll practice on will be about sets. In this video and section, we try to get a feel for what it means for an assertion about sets to be true, and how we would argue that an assertion about sets is true. Like all mathematical investigations, the real way to demonstrate a fact is to write a rigorous mathematical proof for it, and that is where we're heading, but not today. To anticipate proofs, we will look at how we can make a series of Venn diagrams to provide a visual argument for a proposition about sets. Start with an observation. Take three specific sets, A, B, and C. Let's suppose that A is the set 1, 2, 3, B is the set 3, 4, 5, and C is the set 5, 6, 7. Let's evaluate A union with the quantity B intersects C. Substitute in the specific values of A, B, and C. Then compute the intersection of B and C, that is, the intersection of set 3, 4, 5 and the set 5, 6, 7 to get the set 5. Then union that with set A, that is, union set 1, 2, 3 with our previous result, set 5, to get our final result here, the set 1, 2, 3, 5. Now, consider the set that results from quantity A union B intersected with quantity A union C. Take for a moment to read the working out of this operation and convince yourself that it is correct. It's the same answer as the previous. Our observation is that for these three sets A, B, and C, the left side of this equation at the bottom of the slide happens to be equal to the right. Or I suppose another way to put that is that this equation at the bottom of the slide is true. Notice that we have demonstrated this property only for the specific three sets defined here. We're now about to make a leap of abstraction from a proposition about three specific sets to a proposition about any sets. Specifically, it's now reasonable to make the following hypothesis. We suspect that what we saw in the previous slide is true for any sets A, B, and C, not just the specific ones we defined. I say suspect because what we did on the previous slide doesn't prove anything about this general proposition. The really cool thing about this equation is that if it's true, it's very similar to something you should remember from grade school, the distributive law of arithmetic. Since I know the answer, I'll just tell you. It is true for all sets, and we call it the distributive law of sets. And if you were to switch all the unions and intersections to get the equation at the bottom of the slide, well, that one's true too. So sets, in fact, have two distributive laws. But don't take my word for it. Let's demonstrate it, albeit informally. Take a blank Venn diagram with three sets, A, B, and C. These could be any sets. By the way, when we draw three arbitrary sets this way, we are not assuming that they have non-empty overlap. What I mean is that even though B and C are drawn so that they appear to overlap, that doesn't mean that we assume there is something in that overlap region. Regions on Venn diagrams may be empty, and this diagram still works even if the intersection of B and C is the empty set. Even if two of the sets happen to be equal, that's not a problem. If A were equal to B, all that would mean is that all the elements of A and all the elements of B would be concentrated in that region where they overlap. We are now going to shade some regions in the diagram. Since we're interested in A union quantity B intersects C, we will shade A one tint and B intersects C a darker tint. The central region where these two shadings overlap gets the darkest tint. That region happens to be A intersect B intersects C. When you do this on your own, you'll probably want to differentiate shadings by how you orient the lines of the shading. That is, shade one region with lines going from top left to bottom right, and the other shading with bottom left to top right lines. Areas double shaded will then appear with cross marks. Alternately, you could make the shadings different colors. In this case, A union quantity B intersects C is represented by any part of the diagram that is shaded at all. Next, to illustrate quantity A union B intersect quantity A union C, make a diagram where you shade A union B and another diagram where you shade A union C. Superimpose these two diagrams, and the part that is doubly shaded is the set that we're looking for. Now, put these two illustrations side by side. On the left, we have A union intersection of B and C, and that is anything that's shaded on the left. On the right, quantity A union B intersected with quantity A union C is doubly shaded. Since the any shaded part on the left matches the double shaded part on the right, this verifies our proposition. Those two expressions are equal no matter what sets A, B, and C are. Here's another example. I claim that the complement of A union with B is equal to the complement of quantity A minus B. Of course, to say that precisely, I really mean that for any sets A and B, these two expressions are equal. For intuition, consider an example. To make things interesting, we'll use something other than numbers in our sets. Let's say cows and bulls. Suppose we have a herd of cattle named Alvin, Beverly, Camus, Daisy, Eddie, and Gladys. They constitute our universal set. Beverly, Daisy, and Gladys are cows. Call them the set A. This means that the rest are bulls, the complement of A. Moreover, Alvin, Beverly, Camus, and Gladys are spotted. Now, let's work out our equation. First, let's substitute in for A and B. We get the complement of the set Beverly, Daisy, Gladys, union with the set Alvin, Beverly, Camus, Gladys. Applying the complement operation gives us the set Alvin, Camus, Eddie, union with the other set. Performing the union operation gives us Alvin, Beverly, Camus, Eddie, and Gladys. Notice that that happens to be everyone except Daisy. And while we would never come up with this immediately on our own, we can still check and note that the set containing only Daisy happens to be the same as the set we would get if we took the set Beverly, Daisy, Gladys and subtracted off the set Alvin, Beverly, Camus, Gladys. And we care about that because those two sets are the cows minus the spotted ones. We interpret the final answer as the complement of cows minus the spotted, or all but the non-spotted cows. More importantly, here's how we verify the general claim visually. On the left, we have the complement of A lightly shaded, and separately, we have B medium shaded. Now, if we superimpose those two, the union of them is anything that is shaded, bottom left. On the right, A minus B is lightly shaded. Then we turn that around and shade the complement with a medium shade. And now in the end, observe that is the same region that has any shade on the left. So the two bottom diagrams show areas that in the diagrams that match. Here's a final example, and this one we will look at only abstractly. In the previous video, when we defined set difference, say a minus b, we noted that it doesn't matter whether or not b has any elements not in a. Those extra elements don't affect the result of set difference. Stated formally, we mean that for any sets a and b, a minus b is the same as a minus the intersection of a and b. The visual verification is pretty simple. On the left, we shade A lightly and B medium. The overlap is the dark shade. The difference, A minus B, is the area shaded only lightly. On the right, we shade A lightly and give a medium shade to the overlap of A and B. Note that the set A itself is that which has any shade on the right. More importantly, A minus intersection A and B is that which is only lightly shaded, and it is identical to the area on the left that is only lightly shaded. What we have seen in all this is that we can verify set facts with a simple, intuitive visual system, a series of Venn diagrams together with some verbal explanation. I recommend you practice these. Some problems might require more individual pictures than others. When we start writing proofs, you may still find it useful to do visual verifications as scratch work first, as an aid to intuition. The next section switches gears to introduce a second content stream in this course, programming using ML. In the accompanying video, I will also give an explanation of the usefulness of functional programming in ML and the role it plays in this text or course.